A good place to start is to take a look at the optimized 4x4 version we have of the algorithm. What we want to do is translate this to a 6x6x6. If we just treat a 6x6 like a 4x4, the following translation will apply, where the parenthesized moves represent moving both inner layer slices as one, and executing the algorithm on a super 6x6x6 would look like this. It's same proportion, it's more layers turned because it's a larger even cube, but identical to the 4x4 example. The problem of translating this algorithm to higher order cubes is not this, obviously, because everything is fine on the cube. However, if you don't want to apply it to all orbits, each of these are orbits. These two edge pieces are the outer orbit, outermost slice of the cube, and these two edge pieces constitute the inner orbit of the 6x6 because they're innermost slices of the cube. If we were to handle one of these two separately, as in only affect these two edges, or in the other case affect the other two, then we have problems translating it to larger cubes. If we were to translate this to the outer orbit of the 6x6, the only portion of the algorithm that might be a little bit tricky, besides making these turns here just a single slice on the inside of the cube, the tricky part is converting this right here, because we did something different to optimize the moves earlier on. So for the outer orbit of the 6x6, that portion I highlighted previously is equivalent to this, which equals the inverse of this, just by doing it on a cube, a real cube, so you can see the move equivalence, which can be simplified to that. So in effect, this right here is a translation for the outer orbit to the 6x6. Notice that now we have two edge pieces discolored. If we were to translate this algorithm to the inner orbit of the 6x6, those two moves would simply just be this. These two moves right here would just be that. Applying this to the 6x6 inner orbit, still two center pieces are swapped, just different ones, because now it's in a different orbit. So we have a problem, obviously. How do we fix this? Although it's not initially obvious, interior setup moves is our only option if we want to keep a low count algorithm that applies to all size cubes without being forced to solve the centers back after we execute the part of the algorithm on a particular orbit of a big cube. What I mean by interior setup moves is you're actually inserting moves in the middle of the algorithm. And we can see where we might be able to if we just apply the algorithm to a particular orbit in a cube and slowly reverse the moves and trace back the two center pieces that are discolored. So what we can do as a start is execute the algorithm on the 6x6, and then we can trace back the locations of both discolored pieces and take note of their locations and identify them with technical terms so that we can refer back to their locations later. Just for my personal preference, I will just use the translation that I showed you previously to the inner orbit of the 6x6 supercube. First, let's just focus on this piece right here in the top, where it should be a black piece, but it's red instead. We'll get this one in a minute. First, we're just going to see where this goes. This is how the cube is if you were to execute the algorithm without moving it around first. So I'm moving the cube like this. So this is 2F, and it's intersected with the slice 3R, and it's occurring in D. So in technical terms, this piece is located at the intersection between slices 2F and 3R in D. Now since we found that piece, right there, we're going to find the other piece. And now we're going to trace this black piece to that portion of the algorithm. It's right here. So this, it's located at the intersection between slices 3U and 2R in B. Since we know that the portion of the algorithm to insert moves is before the following piece, and there are more pieces afterwards, of course, but this is actually the piece group that we're going to be focusing on, it might be convenient for us to rewrite the algorithm like so. We're just taking all the moves that are before that and writing them on one line, adding a few spaces, and then putting a couple spaces after this piece with the rest of the algorithm. Because what we're going to do is we're going to insert a move here and we're going to undo it here. Our interior setup moves. Just by observation, obviously a red centerpiece needs to go in place of the black centerpiece located at the intersection of the slices 3U and 2R in B, because this is the normal position of the cube, so this is F and that's U and so forth. This is the second piece that we found. This is black, but it should be red because red and black are the two centerpiece colors that are discolored. So if this was red, then red would swap with red, and therefore we would have a pure algorithm. That's basically what I was saying. Conveniently, we can do 2R prime to do this. We can insert 2R prime, and then we can execute the following piece, and then we can undo it before the end of the algorithm. And this is actually the solution that yields the optimal path. So from this point, if all I wanted to do was, okay, and this is the top of the cube, so I'm moving 2R prime down to insert a red here. Okay, now what I'm going to do is execute 3B prime, 3R prime, and 3B. Now what I'm going to do is undo that 2R slice with 2R. Now I'm going to let the rest of the algorithm execute. As you can see, it fixed the problem. Now red swap with red, because now originally we had just 2 red centerpieces swap with each other, but now we have 4. And there are no black involved now. And these remain the same, they still swap with each other. So basically that is the move insertion. Now we take this interior setup move and we can remove the parentheses now. And this again is applied to the inner orbit of the 6x6. The inverse of the setup move cancels with the move after it. That leaves us with a 20 quarter turn / 19 half turn algorithm. The 2R here canceled with the 2R portion of this turn to leave us with just R prime instead of 2R prime, because the interlayer slices canceled with each other. If consecutive slices from the right corner to the middle slice need to be affected, as in, for example, this is the 11 by 11 cube, and this right here is the right corner. If this slice and this slice were affected only, and we needed to apply an edge flip algorithm to those orbits, or if it was these 3, as long as it's something that from the right corner consecutive slices need to be affected, that's what I mean, then the interior setup move can merge with the double turn of L, the double wide turn of L. This right here will cancel with this because the slices are adjacent to each other. The algorithm will actually cancel to 19 quarter turns, but it'll still remain 19 half turns. So for the 7x7, for instance, it would be executed in the following way on the outer orbit of the cube. Because on the outer orbit it's consecutive slices from the corner, and it's not both of them, like if we were to treat this like a 5 by 5. So for this particular case, instead of doing a double turn of the 4 slices and then move this down, an equivalent is just 5L and 4L. It's the same thing. And that's where it merges from 3/4 turns to 2, knocking off a quarter turn, basically. So that interior setup move will cancel, just as I said. Which is pretty neat. Now I'm moving on to the real structure, the outline of the Holy Grail algorithm, as presented on the 7x7 inner orbit this time, without move cancellations. Again, the inner orbit of the 7x7 looks like this, and this is the translation on 2 lines. Technically, shifts are just setup moves which are inverses of the first move of the base. If we go back to that portion of the derivation, this was the base before we did anything. A very familiar sight. From this point, we just took the first move and we made it the last move. So, an equivalent to doing that is, first, adding the setup move 2B prime, and then inverting it at the end with 2B. Because then these 2 moves will cancel. Similarly, you can do the same for all the other shifts. So technically, if we were to take the entire algorithm without leaving out any cancellations like that, if we just had all the setup moves, this is the entire algorithm represented on the inner orbit of the 7x7. It has a lot of symmetry. For example, this piece right here is inverted in this piece right here. This piece is inverted here. This 3B prime is undone here. And then this 3B, which is the next move in the sequence, is undone with this 3B prime. And this 4L2 is undone with 4L2 there. And then this is the commutator that we used at the beginning. It's just now it's translated on the 7x7, so it looks a little bit different than how it looked for the 5x5. And then this move right here is the quarter turn that we added to the base. And then this right here is the interior setup move that we applied just now. So it's a very nested structure. It's very complicated, complex, but the derivation for it is basically easily done just by finding the commutator, applying setup moves to that commutator to get all of the pieces affected by it in the 2R slice of the 5x5, talking about the 5x5, then doing a quarter turn, placing back 2 of the edge pieces and half the center pieces, and then shifting the base until we have a 2 diagonal edge swap finally, and then adding the final setup moves to make it a pure algorithm, and then finally inserting these interior setup moves for larger cube sizes. That's a much easier way to look at it than this way, but this is the structure, the outline of the algorithm if we were to look at it as a whole. So how do we apply this to all size cubes for all cases and all orbits? Maybe it's best to show you on a 7x7 cube. We execute those moves. Right here. After we do the double wide turn of L, whatever slices you pull down, they are the complement of, or they are all the slices that do not need to be affected. So in this case, this slice does not need to be affected since we only want to affect the inner orbit. So we pull that one down. But if this was a larger cube and we only wanted to affect one orbit, then we would pull down more than one and they could be spaced out. But that's what this represents. And then we no longer have that complement anymore. Now from this point, the algorithm just finishes off the same. So we can actually write a general formula for this. I'm going to assign a certain convention to represent moving large portions of the cube so that we don't have to have a formula which depends on the cube size but represents every cube. So in general, if we let star and then whatever it is, if it's lowercase r, l, f, b, u, d, just denoting all of the moves in the notation of sign, let that represent moving half of a cube once, including the outermost layer but excluding the central slice on odd cubes. And if we let star with capital letters denote moving all inner layer slices moved once in the same direction, not including the outermost layer or central slice on odd cubes, still not including that. So like on the 7x7, star lowercase r would just be equivalent to 3r. And star capital R would be 2-3 lowercase r. So using this convention, we're going to still have to have a different representation for odd and even cube sizes because of the central slice on odd cubes, but they're basically the same. For even cube sizes 4x4 and greater, all of these moves should be intuitive based on the convention I gave, except for this right here. This right here represents moving all of the inner layer right slices down, which need to be affected by the edge flip algorithm. And this right here represents the complement of that, or all the slices that do not need to be affected by the odd parity algorithm to be moved down here, because it's r prime. And then here it's the same as this. And for odd cubes, all we have to do is take the even cube representation and just put parentheses around the moves which include the central slice on the odd cube. By observing the general formula, the algorithm being applied to the 4x4 and 5x5 are merely special cases of the overall algorithm, how you apply it to all size cubes, because the move, the complement of the slices that need to be affected by the odd parity algorithm, that is not existent on a 4x4 or 5x5. So that's basically it. Now I'm going to get into explaining why the interior setup move that I did worked, and if there are other possible paths I could take besides that one, and basically explaining why that interior setup move worked and didn't scramble the cube. I will explain the restriction that we have in a lot of detail about those move insertions. So for those interested, keep watching.